Okay.
Yeah. So welcome everybody to a new Origin seminar today. So today we have a talk by Ryan Boyden, who is a grad student here at the University of Arizona, working together with George Eisner, and he's going to talk to us about protoplanetary disks. I would like to remind you to please turn off your audio and video if you're online, because that will help people that have low bandwidth. If you have any urgent question that you would like to ask the speaker, please type it in the chat. Then one of the organizers will try to clarify that question. But you can take it.
Okay. Before I get started, can everybody on Zoom hear me okay? Maybe if we see a thumbs up in the chat.
We get a thumbs up.
Okay, perfect. All right, all set. Okay, thanks for waiting for us to figure out all the Zoom stuff. I think most of you here know who I am, but for those who don't, and for those on Zoom, my name is Ryan. I'm a sixth-year grad student here at Steward, and my research is all about studying protoplanetary disks in young stellar clusters, like the Orion Nebula Cluster shown on the slide here. And I'm very interested in this research because protoplanetary disks are the birthplaces of planetary systems, like our own solar system, and young stellar clusters are the most common sites of star formation in our galaxy. So by studying protoplanetary disks in nearby clusters, we can get a better understanding as to how most disks in planetary systems form and evolve over time. Studying disks in these regions can also give us the ability to probe planet formation processes in environments that are very different from the environments of these more nearby, lower mass star forming regions, like Taurus, for example. And today, I'll be talking about the bulk of the work that I've led throughout the course of my PhD, where I've used radio interferometers like ALMA and thermochemical disk modeling software to constrain the total disk masses, gas to dust ratios, and chemical compositions of a large sample of protoplanetary disks in the Orion Nebula Cluster, or the ONC, as I'll be referring to as throughout this presentation. And we're actually finding through this research that the ONC contains a subset of massive disks with enough material to form giant planets. And this finding has implications for both the evolutionary state of the ONC, as well as the general chemistry of protoplanetary disks in these massive cluster star forming regions. So I'll try to paint a broad picture of all the work that I've done throughout the course of my thesis, these two papers in particular. And towards the end of this talk, I'll be highlighting some new work that I'm leading in other nearby young stellar clusters with the VLA. Okay, so a key property of young stellar clusters that distinguishes them from those lower mass star forming regions like Taurus is the presence of massive stars. So young stellar clusters host these massive O and B type stars that output intense ultraviolet radiation into the surrounding natal environment. And this in turn enhances the local UV radiation field strength towards the positions of other cluster members. And in the ONC, the massive stars are found in the center of the cluster right there, and they're known as the trapezium stars. And this enhanced UV radiation field driven by the presence of massive stars turns out to have a very dramatic effect on the evolution of protoplanetary disks. And to describe this effect, I like to pretend that H.L. Tau, very famous nearby protoplanetary disk in Taurus, I like to pretend that it's located somewhere in the ONC, say right here, for example. And if this were the case, the UV photons generated by these massive trapezium stars, they'd be incident on the surface of H.L. Tau. What happens next is these UV photons, they heat the disk surface, drive disk mass loss, and ultimately reduce the amount of material available to form planets. And this effect in particular is commonly known as external photoevaporation, and we've known about it for many decades now. So Hubble has imaged many young stars in the Orion Nebula Cluster, and these observations reveal that many protoplanetary disks in this cluster are surrounded by these bright ionized structures of outflowing gas, commonly known as proplyds. And here I'm showing a few different HST images of proplyds in the ONC. And I want to mention quickly that Hubble tends to get the credit for discovering proplyds, but it was actually the VLA that found these objects first back in the 80s through these observations probing centimeter wavelength free emission. And I'm mentioning this now because this will tie into some new work that I'm currently leading in other clusters with the VLA. So stay tuned for that. Here I'm showing a couple of different VLA images of proplyds. And with both the VLA and HST, what we're seeing is the same thing. We're seeing these bright ionized structures of gas that are oriented towards the direction of these massive stars, providing evidence that strong UV fields from massive stars are heating the disk surface, driving disk mass loss, and then ionizing this outflowing material. And nowadays, in the era of ALMA, we're able to probe the dust and molecular gas reservoirs of these protoplanetary disks. And we can use submillimeter wavelength measurements of dust emission and molecular line emission to examine how environment effects like external photoevaporation influence the masses and sizes and chemical compositions of protoplanetary disks. And there's been a lot of work over the past decade examining how environment effects influence the dust compositions of protoplanetary disks. This figure here shows the cumulative distribution functions of disk mass derived from measurements of dust emission for many of the different star-forming regions that we've surveyed over the past decade with ALMA. And you see these types of plots very often in the ALMA protoplanetary disk subfield. And for those who aren't familiar with them, just to go over how you would interpret one of these distributions, here I've highlighted the disk mass distribution for the Lupus star-forming region, which is one of these lower mass star-forming regions that lacks massive O and B type stars. So how we would read this figure is, we would say that in Lupus, more than 80% of the disks in the region have dust masses greater than 1 Earth mass. And similarly, more than 30% of the disks in the region have dust masses greater than 10 Earth masses. That's how we interpret one of these distributions. And when we look at them collectively, one thing that we're finding is that disks in clustered environments like the ONC, shown here on the right, they tend to be less massive than the disks found in lower mass star-forming regions of similar age. So both Lupus, shown on the left, and ONC, shown on the right, they're thought to be aged at around 1 million years. But you can see that Lupus has a greater fraction of massive disks than the ONC does. And this is interesting in the context of external photoevaporation, because it's pointing to this idea that strong UV fields from massive stars can lead to a more rapid reduction of protoplanetary disk material. But one thing to keep in mind when looking at these distributions is that they're derived from measurements of dust emission. And protoplanetary disks consist of both dust and molecular gas. And while the dust content of these disks is typically easier to measure and sometimes easier to interpret than the molecular gas content, the molecular gas dominates the mass budget of protoplanetary disks and also sets the chemical landscape of planet formation. So it's still very important that we take the time to understand the molecular gas compositions of protoplanetary disks, especially in these clustered star-forming regions where we think most stars and planets form. And that's where my research comes in. I'm very interested in characterizing the molecular gas content of protoplanetary disks in nearby clustered star-forming regions. And for my thesis, what I set out to do was constrain the molecular gas masses and gas-to-dust ratios of a large sample of protoplanetary disks in a nearby cluster. And I wanted to compare these quantities with the values derived for disks in other star-forming regions to identify differences linked to the stellar cluster environment. And to do this, the first thing that I did was put together a sample of ALMA-detected gas disks in a young stellar cluster. So in particular, I searched for compact disks within these very deep, high angular resolution ALMA observations that map the entire central region of the ONC in both CO and in HCO+. And after searching through literally thousands and thousands of data points, I was able to identify a sample of around 20 protoplanetary disks in molecular gas. And here I'm showing integrated intensity or moment zero maps of the detected gas disks in my sample, where these black contours show ALMA detected molecular line emission, and where the lighter gray contours show ALMA dust continuum emission at around 350 gigahertz. And you can see here that we're detecting disks in both CO and in HCO+, and we're also detecting a large subset of protoplanetary disks in CO absorption. And here, when I say absorption, I mean that the detected molecular line emission is negative. And in a few slides from here, I'll be introducing a concept that we can use to actually interpret these negative emission detections. Before I get to that, a couple more details about this ALMA sample. So we're spatially resolving these disks, typically at an angular resolution of around 0.1 arc seconds, which corresponds to 40 AU at the distance to Orion. But also we're spectrally resolving many of these disks at a velocity resolution of around 0.5 kilometers per second. And here I'm showing moment one maps or velocity weighted intensity maps of these detected gas disks, where this change in color from blue to red along the dust major axes is telling us that we detected the Keplerian rotation associated with this protoplanetary disks. And I just want to emphasize that this is currently the largest sample of ALMA detected gas disks in a clustered star forming region. And so this data set and this sample in particular, it provides a great opportunity to examine how environment effects like external photoevaporation influence the molecular gas compositions of protoplanetary disks. And like I mentioned earlier, I was very interested in constraining the molecular gas masses and gas to dust ratios of this sample of ALMA detected gas disks. And to constrain these quantities, I used the chemical disk modeling software called RAC2D. And these chemical codes are used very often to constrain disk properties from ALMA molecular line observations of protoplanetary disks. So just to go over briefly how these codes work, what they do is they simulate the chemical evolution and molecular line emission of a model protoplanetary disk as a function of different parameters. So disk parameters, stellar parameters, environment parameters, and so forth. What I did with this code was I used RAC2D to generate a suite of around 2 million independent chemical disk models as a function of the total disk masses, both dust and gas. It's a function of the UV and X-ray radiation fields, the sizes of my model disks, the viewing geometries, as well as the masses of the central star. And after generating this large grid of models, I then fitted it to the dust continuum and ALMA molecular line observations of each target in my sample to constrain quantities like the disk mass or the disk gas to dust ratio. And for the sources that are detected in CO emission or an HCO plus emission, this fitting procedure is very straightforward because these chemical disk models, they generate simulations of disk molecular line emission. They don't on their own generate simulated observations of absorption. So I actually had to develop my own procedure for converting these chemical disk model outputs into simulations of this absorption. And I like talking about this part. It's kind of the favorite part of my PhD thesis that I came up with. So I'm going to introduce this new concept that I added to these chemical disk models and also talk about what it means to see something in negative absorption in these young stellar clusters, because we see a lot of them. So like I mentioned earlier, one of the key differences between young stellar clusters and lower mass star forming regions is the presence of massive stars. Well, another big difference is that young stellar clusters are embedded in these giant molecular clouds that can emit very strong molecular line emission over the same transitions that we use to study protoplanetary disks with ALMA. And when a disk is positioned in front of one of these bright molecular clouds, it can really influence the intensity that we observe towards them with a long baseline interferometer. And I'm illustrating those differences with this figure here. So in the top panel, I constructed a model emission profile of a compact disk positioned in front of a very faint quiescent background, which might be representative of the background conditions in a lower mass star forming region. In the bottom here, I've constructed a model emission profile of a compact disk positioned in front of one of these bright extended molecular clouds, where here, the intensity observed towards the positions of one of these disks following the equation of radiative transfer is now the sum of the disk emission and disk attenuated background cloud emission. And if you were to observe these two very different sky brightness distributions with a long baseline interferometric array configuration, which is only sensitive to compact spatial scales, you would get two very different images. So in the top row here, we would get basically what we put in, where the intensity observed towards the disk is equivalent to the disk intensity, which is great because that's why we designed interferometers in the first place, to probe compact celestial objects like protoplanetary disks. But in the bottom row here, what happens is this extended background cloud emission, it gets spatially filtered out in the long baseline interferometric observations. And what you actually observe towards the position of the compact disk is not the intensity of the disk emission. Rather, it's the difference between the disk emission and disk attenuated spatially filtered background cloud emission. And when the background cloud is brighter than this disk, we see this negative absorption feature in our ALMA observations. So it's a combination of radiative transfer effects and interferometric spatial filtering as to why we see these negative absorption detections very common in these young stellar clusters. you have a quick question?
Yeah. Does it matter that some of the cloud might be in the foreground in front of the disk and not in the background?
If that was the case, then we wouldn't see a negative detection, but we would still see positive emission. It would just be attenuated as the emission from the disk travels through that foreground cloud.
Can you rule that out, or?
Well, we think it's a possibility. We think these are detected in absorption because even at optical wavelengths, we see them in absorption with HST, like those silhouette disks. So that's kind of another piece that we have for that. But there's always some possible foreground contamination, even in lower mass star forming regions. Yeah. Thanks for that clarification question. So that's what it means to see one of these negative detections in our ALMA data set. Now I want to talk briefly about how we implement that concept into our model infrastructure. And I'm going to walk through an example of one of the sources that we detected in CO absorption. It's this proplyd known as 173236, where the absorption morphology is very interesting. We only see strong absorption on one side of the dust disk. So the first thing that we do is we use our chemical disk model to generate simulations of CO molecular line emission. I'm showing one example model in my grid here. It's the integrated intensity profile for that model disk. The second thing we do is we obtain direct measurements of the localized background cloud emission towards the positions of all of these different absorption detections as a function of both position and velocity. And currently, there's no publicly available data set that probes extended CO emission over the same transition that we have our ALMA data for, which is the CO 3-2 transition. There is, however, this very nice publicly available data set that has mapped extended CO 1-0 cloud emission in the ONC. And that data set is led by Shou Kang, which I think is somewhere in this room right here. They map the entire central region of the ONC in CO 1-0. And I use that data set to estimate the background cloud intensity towards all these absorption detections in my sample. And you may be wondering whether it's valid to use this different molecular line transition. But I actually use this radiative transfer tool called Radex to show that towards the positions of all these absorption detections under the expected background cloud densities and temperatures in those localized regions, the cloud intensity at both CO 1-0 and CO 3-2 are nearly equal. So we think that it's okay to use this 1-0 transition to estimate the background cloud temperature in 3-2. But we're actually going to be testing this more directly in future work. I'm the PI of a Cycle 8 ALMA program that has mapped large-scale emission in the ONC over the same transitions of CO and HCO plus that we have our ALMA data for. So I'm really excited to work with that data in future work, and that'll allow us to check some of these assumptions that we've made in our current study. So how we construct these simulated observations of CO absorption is we take our chemical disk model, we take our localized measurements of background cloud emission, and then we combine them following the equation that I showed on the previous slide, and I'm again showing in this figure right here. And we do this combination on a pixel by pixel basis. And here I'm showing the resulting integrated intensity map that you get for one of these chemical disk models. And you can see here that does a very good job at reproducing this asymmetric absorption feature that we're seeing towards many protoplanetary disks in the ONC. And the reason why we see this asymmetry is because the cloud intensity is very velocity dependent. So it's only along certain regions of velocity space where we're seeing these strong absorption features in our ALMA data set. So this is just a walkthrough of one absorption detection, and we did this with all of the absorption detections in our sample. And here I'm illustrating the results of our entire modeling and fitting procedure. Each panel here shows the spatially integrated spectra of one of the ALMA detected gas disks in my sample, where these green colors show detections in CO, and these purple colors show detections in HCO plus. And then the black dashed line in each panel shows the best fit chemical disk model that I got for my fitting procedure. And you can see here that we do a very good job at reproducing all of the sources that are detected in CO emission, as well as in HCO plus emission. And you can see here that this procedure that we developed for generating these simulated observations of absorption, they can also match the ALMA data quite well, even in cases where we see strong emission in one velocity channel, but then strong absorption at a different velocity channel. And I did all this fitting procedures on the channel map observations. And if you would like to see what those look like, I can redirect you to the paper that we have, which kind of publishes all of them in addition to this summary plot shown on the slide here. Okay, so one of the most interesting results that came from fitting and deriving best fit parameter values pertains to the derived gas to dust ratios. So in this figure here, I'm showing the best fit gas to dust ratios and their uncertainties derived from this chemical modeling procedure for all of the disks in my sample. And you can see here that nearly all of the derived gas to dust ratios are consistent with or somewhat larger than the canonical ISM value of 100. And what's interesting about this result here is that these gas to dust ratios are systematically larger than the values derived for disks in lower mass star forming regions from similar chemical modeling of CO or CO isotopologues. In many of these low mass star forming regions, like lupus shown here, disks are found to have these low CO-based gas to dust ratios, sometimes as low as 10, and sometimes even as low as 1 or even lower. And one of the leading explanations for these values is that these disks actually have low amounts of gas phase CO, meaning that the CO content that they initially inherit from their parent molecular cloud is physically and chemically reprocessed in these disks as the disks evolve with time. And this means that if you were to underestimate the amount of CO reprocessing in your chemical modeling infrastructure, which what we think is going on in this region, what that would mean is that you would underestimate the gas masses and gas to dust ratios derived from CO observations alone. So uncertainties surrounding reprocessing of CO is a kind of a big challenge in the protoplanetary disk subfield. And one thing that we're starting to do now to get a better handle on the amount of CO reprocessing in protoplanetary disks is we're starting to use other molecular tracers like N2H+ or C2H to get a better handle on the abundance of CO in protoplanetary disks so that we can better measure gas masses towards those objects. And before I move on, I like to acknowledge that it's still unsettled whether or not these disks are actually prone to significant chemical reprocessing. And I say that because recent work done by Dingshan and Ilaria Pascucci over at LPO have shown that when you start to include grain surface chemistry at a higher level of sophistication into your chemical modeling infrastructure, you can actually get higher CO-based gas to dust ratios than what's being shown from these earlier studies. But in the context of this CO reprocessing scenario, these higher values that we're deriving towards disks in the ONC, it suggests that these sources are less prone to that reprocessing of CO. And one possible explanation for this difference pertains to the measured disk size distribution in the ONC. So in this figure here, I'm plotting measurements of disk radius derived for each target in my sample, plotted as a function of projected separation from the most massive O star in trapezium, the star Theta-1 Ori C. Many protoplanetary disks in the ONC are found to be quite compact with radii of 50 or less than 100 AU. And these sizes are smaller than the values derived towards those disks that are found in lower mass star forming regions and prone to that reprocessing of CO. And this difference here is often attributed to the presence of massive stars in the ONC that can strip the outer regions of protoplanetary disks of planet-forming material. But this difference here is also interesting in the context of protoplanetary disk chemistry. And this is because it's these outer regions of protoplanetary disks where gas phase CO is thought to freeze out onto dust grains and undergo much of that chemical reprocessing. So compact disks in the ONC may simply lack those cold outer reservoirs, and so they maybe harbor these warm environments that enable CO to retain in abundance close to its initial ISM-like value. Do you have a question back there?
I think you mainly cleared it up there at the end. So
Okay.
You kept referring to reprocessing. So freeze out, is that the main effect? Or
That's one of the main ways that we think CO is reprocessing. Ionization is another one where there's really intense levels of cosmic rays in protoplanetary disks, which is still under debate, that can also reprocess CO in gas phase. But freeze out is one of the more popular ideas, what we think is going on. And Sebastian Kreit's done some work on that as well. But yeah, so that's one. So this difference is interesting in the context of protoplanetary disk chemistry. And I also think this result is kind of advantageous because it's suggesting that in young stellar clusters like the ONC, we might not have to worry as much about all these uncertainties surrounding CO depletion when trying to derive gas mass measurements from observations of CO or HCO+. So you can almost be confident in the gas mass measurements derived from thermochemical modeling in these young stellar clusters. This also happen to be the most common sites of star formation in our galaxy. And in terms of the disk masses that I'm deriving from this chemical modeling, I'm showing those in this plot here for, again, each target in my sample. And the uncertainties on these gas mass measurements, they can be very broad due to the high optical depth of the molecular lines that we're modeling. But we're still finding at this current level of precision that many of the derived gas masses are greater than the mass of Jupiter. And this difference is interesting in the context of the stellar cluster environment, because it's telling us that even though things like external photoevaporation are operating in the ONC, this cluster still contains a subset of disks with enough material to form giant planets. And there are a couple of different reasons why we might expect massive gas disks in the ONC in spite of this anticipated environmental impact. One possibility is that the ALMA detected gas disks in our sample are younger than other cluster members in the ONC. And what I mean by this is if you were to plot the positions of individual stars in the ONC on the HR diagram, like Min Fang, a former Alien Earth's team member, has done previous work, what you would see is a pretty large spread in luminosity, several orders of magnitude. And in young stellar clusters, one possible explanation for these luminosity spreads is a spread of stellar ages. So if the targets in our sample were younger than other cluster members, and say somewhere up here on the HR diagram, this would mean that they would have undergone external photoevaporation for a shorter duration than the majority of targets in the ONC, which could explain why we're seeing a small number of massive disks with our current ALMA observations. But it's worth noting that it's still up for debate whether or not there actually is an age spread in the ONC, because Min Fang actually argues that it's circumstellar disks and star spots and things along those lines that are driving this luminosity spread, not a stellar age spread. So with that being said, another possible way that we would get massive disks in the ONC at this current point in time is that external photoevaporation has recently begun operating in the entire cluster. And what I mean by this is, if you remember from earlier, stellar clusters, they form out of these dense clouds of molecular gas. And recent simulations coming out of Tom Haworth's group have shown that this dense gas can actually shield newly born cluster members from those strong external UV fields for as long as 500,000 or even 700,000 years. And these new simulations underscore how stellar ages are likely to overestimate the actual amount of time in which protoplanetary disks undergo external photoevaporation in young stellar clusters. So if shielding played a very important role in the early evolution of the ONC, this could mean that external photoevaporation turned on like 500,000 years ago instead of 1 million years ago. And if this were the case, we might also expect massive disks in this region at its current age of around 1 million years. And I think an increased sample of disk mass measurements, in particular gas mass measurements, would help determine which one of these scenarios is more likely. If we were to detect an increased sample of lower gas mass disks, this might point to this age spread scenario more so than the shielding scenario. And then vice versa, if we were to detect more massive disks. So before I talk about some of the new work that I'm leading with the VOA, I want to highlight one last interesting aspect that came out of this chemical disk modeling, and it pertains to direct measurements of stellar mass in the ONC. So typically, how we measure the masses of pre-main sequence stars is we take measurements of their effective temperature and their luminosity, and we compare these quantities with the values predicted by models of pre-main sequence stellar evolution. And through that comparison, we're able to derive best fit stellar masses and best fit stellar ages. Well, this technique only works if you can obtain reliable measurements of effective temperature and of luminosity. And in young stellar clusters, we can't always do this actually, due to things like the increased nebulosity in young stellar clusters, as well as the increased levels of extinction observed towards localized regions of these clusters. So what that means is that we need an alternative way to measure stellar masses in these young stellar clusters. And one possible way to do that is through modeling the Keplerian rotation of protoplanetary disks. And this is because the Keplerian velocity field of protoplanetary disks is set primarily by the central stellar mass. And through the modeling infrastructure that I developed, I was able to dynamically derive stellar masses for all of the disks in my sample. And I'm showing these measurements, these red diamonds right here. These blue circles show dynamical mass measurements that I obtained from an earlier study using a much simpler kinematic disk model. And then these orange data points show the stellar masses that are derived from those comparisons with pre-main sequence evolutionary tracks, where these different markers are showing what you get for different models, all of which make different assumptions about the star. And again, here you can see that we can only show these orange markers for the subset of targets with spectroscopic data, and we don't have all of them, even for our sample. And one thing to note, or that we found, is that we see a pretty good agreement between the dynamically derived and spectroscopically derived stellar masses for all of the targets in our sample, or for most of them. Typically, we find 1 or 2 sigma agreement between these two types of mass measurements, except for this one source here, which I don't want to talk about now, but I'm happy to talk about more if you ask a question about it. But anyways, and to me, this kind of just reaffirms that we can use dynamical mass measurements to complete the census of spectroscopic masses in young stellar clusters. And one thing that I'm really excited to do in future work is do this for those localized regions of the ONC where we can obtain reliable spectroscopic data. And I'm very excited to see how the inclusion of these additional stellar mass measurements affect some of the interesting correlations that we've seen between disk properties and stellar mass in the ONC with our ALMA surveys. Okay, so in the last few minutes, thank you for still being here. I'd like to talk about some new work that I'm leading in the VLA and that I'll be continuing leading in future years. So like I said, we have a pretty good understanding of which disks in the ONC are injecting mass due to the presence of massive stars. And we know this because we have a good census of proplyds in this cluster in particular. What I'm currently doing with the VLA is I'm leading multiple programs as PI to complete the census of proplyds in the NGC 2024 and the NGC 1977 clusters. Both of these clusters are in the Orion molecular cloud, and they're interesting in different ways. So NGC 2024 is thought to be the youngest cluster in all of Orion, with an age of less than 500,000 years. And NGC 1977 is thought to be this intermediately irradiated cluster, having a UV environment that's stronger than the environments of lower mass star forming regions, but also weaker than that of the ONC. And recently, candidate proplyds were found in both of these young stellar clusters, raising the possibility that external photoevaporation is operating even at early evolutionary times, as well as in these intermediate irradiated clusters. However, the HST data used to find these proplyds, they only targeted a small fraction of stars in the cluster. So if we want to get a better handle on how prevalent environment effects are in these clusters, we really ought to know all of the disks in these regions that have these proplyds. In my VLA observations, they've mapped the entire regions of NGC 2024 and NGC 1977 over multiple radio continuum bands. And these data are going to enable me to identify all disks in these regions that are emitting strong free emission indicative of proplyds. And I'm showing example VLA images of proplyds on the slide here, and I already found new ones in NGC 2024, kind of showing that external photoevaporation is really prevalent in this young stellar cluster. So I'm excited to continue looking through this data over the coming months and years. And that's really all that I prepared for everyone today. So thanks for sticking around and for listening to my thesis work. Yeah, and I'm happy to take any questions on Zoom or in person.
Are there any questions in the audience or online?
Think so?
Yeah, great talk. I'm curious about the R gas. You mentioned the radius of the gas you mentioned in your previous slide. Do you
Yeah, I'll go to
have an
it.
idea of what is then measured? Like, is this like 98% the gas?
Oh, yeah. Yeah, we used a 98% cutoff. Yeah. Yeah. I think some studies will do 68% or 95 or 98%. We try to give the most conservative estimate of how spatially extended they'd be because they're small. So we wanted to make sure, you would encapsulate that.
So for these disks you studied in the ONC, do you see the dust structures, or is it more like one disk is like a big sofa?
Do we see substructures in these disks?
Yes.
So at our spacer resolution, which is about 40 AU, we don't see substructures. But that's also partially due to the fact that even these dust disks are really compact. Like most of them are like less than 25 AU in radius, or less than 40 AU in radius. But if we saw, a very extended dust disk, like if there was one at 300 AU in radius, then we could see substructure, but we don't. And there are some theoretical studies claiming that you shouldn't expect a lot of transition disks in young stellar clusters. But regardless of that, we don't see any in our ALMA data.
Yeah, we have a question online from Joan.
Okay.
Joan, would you like to unmute yourself and ask it yourself, or should I ask it?
I can.
Oh, I'm glad to. Can you hear me?
Yes, we can hear you.
Yeah, wonderful talk. Thanks a lot, Ryan. I just had two questions.
Okay.
First one was about the gas to dust ratio. And I'm not sure if I heard you correctly, but did you say that we understand the gas to dust ratio in the ONC of ONC disks better than maybe those of lower density clusters?
What I meant to say was we think that these disks are less prone to that chemical reprocessing of CO than the disks in lower mass star forming regions, where that is kind of a big uncertainty in how we infer gas to dust ratios in lower mass star forming regions. So we think if that degree of uncertainty is smaller, then we might be more easily able to derive gas to dust ratios in the ONC, and we're finding that they're around 100. Does that clarify your question?
Sort of, but I guess I'm surprised by that because of the complication of the higher irradiation environment, which I thought would have made it more difficult. Is there a reason why? Is it, I guess, they're less processing perhaps because the disks are warmer and there's less freeze out, or is there a physical reason why?
That's one reason. Yeah, we think that that's going on because many of our disks are small and they lack those outer reservoirs at like 200 AU where the disks are quite cold. So that's one attribute to why we think that they're less prone to that reprocessing of CO.
Great, that makes a lot of sense. My other question, very simple. Lovely measurements of the stellar masses, and I was wondering whether things like outflows might play a role in complicating the gas dynamics. Do we have to worry about that, or not so much?
Yeah. So there are a couple of detections that we found in our first paper that we think might be exhibiting kinematics indicative of outflows, but we excluded those from this current sample. So we looked at that a little bit, and we removed those one or two sources. We think that these are Keplerian disks because we're again seeing that change in its velocity gradient along the dust major axes, whereas with an outflow we might expect it in a perpendicular direction. So we tried to sort through that when creating this sample.
Awesome, thank you.
Yep. All right, more hands from the student.
We have a question from Andrea. If you would like to unmute yourself.
Yes, hi, can you hear me?
Yes.
Hi, yeah, great talk. I have also two questions, if I may. One is, so the disk in the ONC, they are smaller and more massive than the disk in low mass star forming region. Do they mean they are gravitationally unstable, or they are just too hot for being unstable?
We haven't done that calculation, but I'm happy to look into it and then follow up with you on that. Yeah. I haven't looked into it yet, though. Thanks.
The other question, if I may, is in the OC there is diffuse free emission. Does that affect your continuum estimate and the dust mass estimates?
Yeah, so when we fitted our models to the dust continuum observations, we actually fitted to just the dust continuum fluxes, where we subtracted out the free contamination using those VLA data. So we accounted for that, because if we didn't, yeah, you would infer, a more massive disk from dust plus free emission versus just dust emission. So we tried to account for that in this modeling. Yes.
Okay, thank you.
Yep.
Okay, then we have another question online from Bennett.
Yeah, in your estimates of dynamical mass, you said that you had one outlier at HC253, and to ask about that in questions, what do you have to say on that?
Yeah, so I'm really glad you asked that. And I'm on the right slide. So that target is on a very strange position on the HR diagram. If you can see my slide, it's this number 334. So it's a cluster member that is very subluminous compared to all the other cluster members in the ONC with the same spectral type. So we think that there's something going on with the spectroscopic data for this source in particular, something like maybe a highly inclined disk is obscuring starlight from this source and affecting the spectroscopic stellar mass measurement. So we think that is why there's such a big discrepancy for that one source, because of potential issues with the spectroscopic data. Yeah. And then the reason why I have different results from my older study is because in that study, we didn't introduce this modeling of absorption. And that source was that asymmetric absorption profile, where a simple intensity profile wouldn't account for that. So both my dynamical mass measurement in 2020 probably had some issues, and then we think something is going on with the spectroscopic data. And that's all driving that really discrepant result for that one source. Thanks for asking that question. Yeah.
Yeah, can you go back to the gas to dust ratios again?
Yeah, sure. I'll add the lupus one in there too.
So obviously measuring gas to dust ratios is very challenging, and I think that's evident by the scale of the error bars on the log plot here.
Yeah.
But I'm wondering if you just actually explain what these error bars are. It looks like some are lower limits, some are upper limits.
Oh yeah, so
confusing to me.
So
they're both upper and lower.
Yeah, so like I said, many of the derived gases, just not all. So now when we generate these grid of models, we can only generate so many models. They can take anywhere from a few hours to several days. So our grid is finite, and we only consider gas to dust ratios from 10 to 10,000. So in this case, within our confidence interval, those outlier points were in there. And for those couple of sources, we didn't really feel it was necessary to add, 100,000 more models or more just to constrain that one data point. So they're upper and lower limits due to our finite grid.
But then you still favor a very high gas to dust ratio based on those symbols.
Yeah, but we also did like a parameter space exploration earlier, showing that gas to dust ratios of 1, for example, majority of our targets, they wouldn't match those sources. And we tried to encapsulate that just from including this lower point of 10. So this one isn't within the confidence interval, but because it's the lowest point in our grid, we have to include it in our uncertainty estimate. So we're very confident that they're all greater than 10, most of them, and hence consistent with ISM values. But yeah, the precision is low, and we're hoping, with better ALMA observations, if people, they rank our proposals highly in attack, we'll get those data to get even better precision. Yeah.
A follow-up question.
Yeah.
Which line do you expect we can observe on ONC for those optically thin lines?
Yeah, so obviously it'd be great to do the standard 13 CO and C18O, but there you would maybe run into some challenges with cloud stuff like I talked about earlier. We're really excited about HCl plus actually, and maybe other kind of high critical density tracers like that. They're less prone to some of those cloud effects in most regions of the ONC. And we're able to, constrain things at decent precision with HCl plus already. So we're excited to try combinations of multiple relatively bright molecules. It might be hard to go for C18O at this distance if you want to get really good data. Yeah.
Okay, if there are no more questions anymore, then let's thank Ryan again for his talk. And I hope to see everybody again next week for our next Orchid seminar.
Oh, look, Nick's on this. Cool.
I didn't know.